again, may seem kind of random, but it's all going to tie together. And I decided, so especially today, since normally this is a kind of class where I would write on the board, but in order that we can have a good recording, so that y'all can refer to the recording later if you want, I'm going to write it on my, I'm going to write it on here, and that way we'll have a PDF of it, and we'll have, I'm recording a video, so even though I personally really like writing on the chalkboard, but for your sake. All right, so we're going to talk today about the Lambda calculus. The Lambda calculus is something that, in one sense, you already know it a little bit because every time you've used a Lambda, I mean, you kind of understand how Haskell, function application works and stuff like that. But Lambda calculus really forms the basis for Haskell and several other functional languages. It's very interesting because it actually is it's kind of a direct bridge between the theoretical and the practical. So you may know of Turing machines. Like if you've taken theory of computation, you've seen Turing machines, maybe you've even just heard about them. Turing machines are, one kind of possible fundamental model of computation, but they're like entirely theoretical. Like no one actually would ever program a Turing machine directly, right? It's extremely tedious. They're not really like theoretically elegant. They're kind of just like, I mean, Alan Turing was amazing, but they're kind of a hack. In the sense that, like, yes, technically they can do any computation, and I understand how he got to that definition, but they're not really good for anything besides like proving theorems and thinking about kind of theory. Lambda calculus was actually developed like exactly around the same time. So at the same time that Alan Turing was writing his PhD thesis, this is like the mid-1930s. Alan Turing wrote his PhD thesis about the Lambda calculus. There's this guy named Alonzo Church who developed the Lambda calculus, kind of for some similar reasons. And both of them can be used as a fundamental model of what computation is. And actually Turing, in like 1937 or maybe even 36, when he saw Alonzo Church's definition of the Lambda calculus, he quickly wrote a paper proving that Turing machines and Lambda calculus are equivalent. Like they're equivalently expressive. Anything you can do with one, you can do with the other. However, right, unlike Turing machines, Lambda calculus is actually practical, right? So Haskell literally, like, when it gets compiled, it compiles it down to kind of a souped-up version of the Lambda calculus, and then like further compiles that. So as a kind of model of computation, it has some really nice properties. It's very interesting. It's also very, very simple, and so it's kind of surprising how little you need to be able to do whatever computation you want. Okay, so that's what we're going to learn about. And I'll probably talk about some more history next time, but so basically the Lambda calculus. So Lambda calculus is basically a stripped down programming language with only functions. Okay? Forget about having ints. Forget about having algebraic data types. Forget about having if statements, booleans, nothing. All you have is functions. And it's like, can you actually do anything with that? Turns out you can. Most programming language features could not just by themselves. Like if you're like, okay, let's throw away everything, but we'll just keep int. Well, you can't really do much if all you have is int, right? It's like, well, I have a number. I can't even add them because if I'm at plus, I just type it. Right? So it turns out with only functions, you can do kind of anything you want. So let me define the syntax of lambda calculus terms using a little recursive grammar thing like we've done before. So T stands for an arbitrary lambda calculus term. So one thing it could be is a variable. It doesn't have to literally be the letter X. It could be basically any. We'll just use like lowercase letters to stand for variables. Any variable name you want. Or it could be the symbol lambda followed by a variable, followed by a dot, followed by, when I say T, I mean recursively there's, any lambda calculus term you want to be there. Okay, so this is called an abstraction, right? Or you could just call it a lambda term. Or it could be, I'll put T1, T2. So it can just be two terms next to each other. And I put the 1 and 2 just to emphasize they can be different, right? They don't have to be like the same term. But ultimately, it's again just recursive, like it's just two terms. So this is application. Right, application as in function application. And this is exactly the notation that Haskell uses for function application, right? You just put things next to each other. That's function application. Okay? That's it. That's the entire syntax of the lambda calculus. So, for some examples, right? These are also like, X. That's a lambda calculus term, right? Or I could use a different variable like F. That would be a lambda calculus term. I could say lambda X dot Y, right? So I'm saying, okay, lambda X dot something is a lambda calculus term, and then that something I'm choosing to be a variable. So that's a lambda calculus term. Or I could say like lambda X dot XY, right? So that's saying, all right, I have a lambda something. That something is going to be an application, and then those terms are going to be both variables, right? Or, okay, let's do something, F lambda X dot for example, okay? Here I have to use some parentheses because, like, for example, so ultimately what is this? This is like, at the top level, this is an application, right? It's this lambda calculus term applied to this lambda calculus term. And then what is this one? This one is also an application. It's an application of this variable F to this term. This term is a lambda, and so on, right? We need the parentheses because otherwise it's kind of ambiguous. What do you mean, right? Really, these are trees. So really, this really means, so I'll write like, I guess I'll write app for application. Another application. F to lambda X. D applied to V, and then over here we've got lambda V. Lambda W. Okay. Does this make sense? Fundamentally, this term kind of means this, right? This recursive definition is kind of defining a certain kind of tree, right? It's like, well, your leaves are variables, or you could have a node with two branches and two subtrees, or you could have this special kind of node with a lambda that has a variable and then it has a one subtree, right? So it's really defining a kind of tree, but when we write it out on paper, we have to use parentheses to disambiguate, right? Just like we usually do with expressions. Does this make sense so far? I want to make sure that if there's any questions. Yeah, why is it not F on the two things? Just F or
to it being like F, like having an application, the two things, I don't know how to say it, so like, there's F, why is it not F on the like two sides of parentheses, like that and the...
This and this?
Yeah.
Oh, just because of where the parentheses are. So notice, let's see, these parentheses go together, right, then these ones go together, and then this one pairs with this, right? So this F and this are inside parentheses. Yeah, if I didn't have these parentheses here, well, then we have to talk about kind of conventions in terms of when can you leave out parentheses and what does it mean. But yeah, like I could have. I mean, so fundamentally, right? The way I've defined this grammar, there's no way to talk about something being applied to two things, right? Just like actually in Haskell, right? We can say, oh, F applied to X, Y, but really that means F applied to X, and then that thing applied to Y. So you can really only apply one thing to one thing. It's the same here. Other questions? So yeah, and I do want to emphasize, right? Remember, Haskell is based on this. So like, if you take Haskell, all the Haskell you've been practicing, and you take out stuff like int, and you take out like pattern matching, right? But anytime you have to worry about like, where do I put parentheses? You know, is it like this applied to this, or like, right? When you write a lambda, all that stuff, that's exactly what's going on here. So all your intuition that you built up for that carries over. Okay, so that's what lambda calculus terms are. And so here's a few conventions. These are just conventions to save ourselves some parentheses, right? They're not like fundamental, but just so that we don't have to write quite so many parentheses or quite so much tedious detail. A few conventions. So lambda scopes as far to the right as possible. So, for example, if I have lambda x dot fx, it means lambda x dot parentheses fx, not lambda x dot f applied to x. Okay. So when I just have a lambda, the stuff inside the lambda is like you go as far to the right as you can. Everything after the lambda is like part of the lambda. Right? So it doesn't mean this, where you would like stop and then have the lambda applied to the x. Okay? Because it's kind of less common to write something like this. It's more common that you would have a lambda and have a bunch of stuff that's inside it. So that's the convention. So nested lambdas can be abbreviated for example, lambda x dot lambda y dot lambda z dot z can be written lambda x y z dot. And this really goes back to, I mean, this we talked about something similar in Haskell the other day, where what is this? Right? Remember, we're thinking a lambda is like a function, right? So this is like a function that takes an argument x and returns a function. And that function it returns takes an argument y and returns a function, which takes z and returns z. So we can think of it that way. We can also think of it as a three-argument function, right? But that's curried. And so that's kind of why we use this notation as an abbreviation, because we can think of it as like a single lambda that takes three arguments. But really that's the same thing as a lambda that returns a lambda. Okay. And finally, just like in Haskell, application associates to the left. write a string of things next to each other, it really means applying them kind of from the left. Right, because again, maybe f is like a function that takes 3 arguments, which really means the function that takes 1 argument, and then that is a function that applies to this, which is a function that applies to this. Okay, so again, that just, all that does, all these conventions do is kind of let us write lambda terms with fewer parentheses and with some abbreviations. It doesn't fundamentally change what they are. Okay, so I'll say the Greek starter star can be written. See, can I get that on the screen at the same time? Maybe if I well, maybe like full screen or something. That was underwhelming. That went further. It's like, what? How does full screen not mean hide the toolbar? But I can, okay, I can see it. So this thing up here, so notice how first of all, it's like f applied to something, and then that whole thing is applied to this, right? That's a left nested application, so I actually don't need, like these parentheses I don't need. I don't need these parentheses around the VB because, right, whenever you have lambda x dot something, that, like everything to the right of it is going to be part of lambda x. And then these lambdas here, I can like abbreviate as 1 lambda with 2 arguments. So I can write it f lambda x dot v and the dw dot v. Right, it means the same thing. It's a little bit easier to write, or to read. I can't get rid of any more parentheses, right, because if I took these parentheses away, right, then it would look like all of this stuff is part of this lambda, which it's not. And if I took these parentheses away, I guess, well, no, it would look weird. It would like, maybe I could technically, for some reason I feel weird about that. I'm not sure why. Whatever. If in doubt, you can always use more parentheses, right? And if you're not like super confident with these conventions, then definitely do start by writing all the parentheses, because like mixing up your parentheses or like forgetting parentheses is the easiest way to get screwed up when you're doing something like that, right? So. Okay, so how does this correspond to a programming language? So far, like we know the syntax, right? So we know how to kind of write programs in this language, but how do they actually run? That's the next thing we need to talk about. And you probably, I mean, intuitively, right, this means a function that takes an argument x and returns t. And this means applying a function to an argument. So we kind of already have an intuitive idea of how this ought to work, right? When you apply a function to an argument, the argument kind of like becomes, like if I take this thing, lambda xt, and I apply it to something, the thing I apply it to is the argument, and so I put that in place of x. I say, oh, x was standing for whatever the argument is going to be, and now I know what the argument is, so I put it in for x. That's the idea. So let's see how to make that a little more formal. Okay, so to talk about that, we have to talk about so when I write like actually, okay, what order? I don't think what order I'm in. Okay, here's the idea. Let me give you the big picture, and then but there's like some details we need to go back and talk about because, and I could just start with the details, but I think it might feel like pulling a rabbit out of a hat. You're like, why are we talking about those details? Like, what's the point? So let me tell you the big picture, and then I'll tell you what kind of what goes wrong, and why we need to go back and be a little more careful. Okay. idea, right, lambda x dot t is a function which takes an argument named x, and returns t, right? And then, of course, x may occur inside t, right? That's the whole point. If x doesn't occur anywhere inside t, we'll find it's just a function that ignores its argument and then returns t no matter what. That would be kind of boring, right? The point is you can have a function that takes an argument and then uses that argument somehow, okay? So when we apply some lambda, like lambda x dot t, to an argument t2, the idea is, well, this is a function that's waiting for an argument, and we've now given it an argument. And so we're just going to take whatever t is, and we're going to replace, everywhere that we see x inside t, we're going to replace it with t2. It results in t, right? That's the output of the function is t, but with x replaced by t2. Does that make sense? So, for example, if I have like, lambda x dot lambda y dot x applied to lambda z dot z, right? Again, I've got a function that's expecting x, and it's going to return lambda y dot x. So, and I'm applying it to something, so I'm going to return lambda y dot x, except, well, x we now know is lambda z dot z. So I replace x with this, and I get lambda y dot lambda z dot z. Okay. Right, and maybe it's more helpful to think about it without all these lambdas everywhere. In Haskell, if I had something like lambda x dot x plus 5, and I applied that to the argument 3, right, that should give me 3 plus 5, right, because I output x plus 5, but x is replaced by this argument 3. Right, we don't have numbers in plus in lambda calculus, but this is the same idea that happens in Haskell. Okay, any questions so far? Andre, any question? This example? So I have a function here that says it takes an argument x and returns lambda y dot x, right? Make sense? So I take that function and I apply it to an argument. The argument I'm applying it to in this case is lambda z dot z, right? So it's like when you call a function and you pass it. I'm calling this function and I'm passing it lambda z dot z as its input, as its argument. So that is now, when that function runs, like that, this is now the value that x is going to have. Right? Just like when you write a function and you say, fx equals blah, 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 and you say f3, that means you're saying, all right, when this function runs x, the input x is going to be 3 this time. If you run it again, it might be something else. But. So the way I do that here is I just say, all right, let's just say, I get the output of that function, lambda y dot x, but I've replaced x with whatever input was. Does that help? Okay. Any other questions? Yes, Iris.
Would it be the same thing if the second x was like
So you mean if I had lambda x here,
Yeah.
and then I had lambda y dot a?
Yeah.
Yeah, good question. So in that case, this would be a function that ignores its input, right? Because it takes something called x, but it doesn't use x anywhere inside here. And so then it would just return lambda y dot a, and like this would just kind of go away because it got ignored. Yeah, good question though. And actually, another question you could ask, which is kind of similar but has a different answer, is what if you had lambda a dot lambda y dot a? Would that act the same way? It would, right? Because what this x is named, what this argument is named, doesn't really matter, right? It's just like it takes an argument, and I happen to call it x just because I need to call it something, right? But as long as I use it in the same way, it doesn't matter. And so that's actually the next thing we're going to talk about. Someone talk about next. Yeah, so a few caveats slash technicalities. Basically, here's the deal, right? You now understand the idea of how this is supposed to work. There's a problem, which is just the fact that we have to pick actual names to stand for things gets in the way of a lot of stuff. Because what if we happen to pick the same name for two things? Or like, like Silas was saying, what if like, something has a different name or the same name? Like, it actually causes some problems. So we just have to like be a little careful about that. So that's what we're going to talk about next. So one is called alpha equivalence. So it asks me why it's called alpha equivalence, just like Weber talked about a bunch of different kinds of equivalences, like to choose Greek letters for them. So this is not letter alpha, but that's what everyone calls it. So this basically just says the name of the name of a variable in a lambda doesn't matter. So for example, lambda x dot x is the same as, in some sense, lambda a dot a. Right? Those represent the same function, even though they're written literally differently. But the name doesn't matter, as long as we kind of rename everything consistently. So I'll just say as long as we rename everything consistently. Okay, so, or as another example, lambda x dot yzx equals lambda q dot yzq. Right, because of this x, I changed the name of this x, so I have to also, like this x is referring to this one, right? Because it's like this is the output of the function. This x here is referring to this x, so if I rename this x, I have to rename this one too. And so this is the same thing. Y and z though, I can't rename because we don't know what they're referring to. They're referring to something else kind of outside in the context. Maybe there's some global variable, or there's an argument to some function that we're kind of in the middle of evaluating right now. And so I can't just change y or z because I don't know what they're referring to. So that tells us there's something different about x versus y and z in this example, right? Because x, we know what it refers to, it's right here, and y and z, we don't really know what they're referring to. You could think of them as undefined, or you could think of them as just referring to something else in the bigger context that we can't see right now. So this is the idea of bound versus free variables. So being undefined, or refers to some external thing. Okay, so for example, if I have, I don't know, lambda x dot y applied to lambda y dot z y x. So let's think about this. So this x here, we'll start from the end. This x here, is that bound or free? What do you think? It's bound, right? Because it's inside this lambda here, this lambda x. Like all of this stuff is inside this lambda x, and so this x refers to this. Like, draw a little arrow actually, just to show like, yeah. When you see this x, it's really talking about, you know, whatever the input was to this lambda. That's what I'm talking about. That's bound. What about this y? Do we know what it's referring to? Yeah, it's this right here, right? So that y is bound. What about z? I don't have any lambda z anywhere, right? So this is free. So maybe I'll just put like a, I'll just put like an arrow pointing out, up, because it's free. So this is like green is free, and blue is bound. And what about this y? Here, what do you think?
I think it's free.
Think it's free? We don't think. Andre agrees. Yeah, it is. So even though I have a lambda y here, right, this y is not inside that lambda. So this y is not referring to, you know, this. It's referring to something else outside, right? I mean, it's like scopes, right? So if I have, yeah. Okay, does that make sense? So one way you can think of it is think about like going through from the outside to the inside. And every time you see a lambda, you kind of remember, oh, when I'm inside this, I now have another variable that's defined, right? So now that I'm inside this lambda x, I know that x is defined, right? And then I see a y, and like, is that in my set of things that are defined? Nope. I haven't talked about a y, so that's free. And then I go inside here, and I say, I have a lambda y. Now I'm still inside this lambda x. Now I'm also inside this lambda y. So now I have two variables that are defined, x and y. And when I see these y, this y and this x, I know that they're referring to those, but z I haven't seen, so that's free. And you can kind of recursively go through a term like that and figure out which things are free or bound, right? It just has to do with, you know, what lambdas are they inside. Okay. So the reason one reason we need to talk about that is going back to the idea of substitution. We need to be careful about which things are bound versus which things are free. So, how do I say, what's the problem? So here's a problem. What is so what did I write? I didn't write the notation for this today. I'll just say, if we substitute lambda z dot y z we could just literally say, well, okay, everywhere I see q, I'm going to replace it with lambda z dot yz. And I'm just going to like go through and everywhere I see q, I just replace that, and I replace this, and I'm done. Okay? But that would be wrong, and there's actually two things that are wrong here. Or two things that would be wrong. So do we get lambda y, lambda z dot yz, lambda q dot lambda z dot yz? Right, so that would be what I would get if I just literally went through and everywhere I saw q, I replaced it with lambda z dot yz. Anyone want to guess what some of the problems with this are? Yeah, 100.
Are those keys for output?
Say it again?
Are those keys for output?
Aren't they the output? What do you mean?
What if next one lambda y dot q isn't y given
Yes. I'm not understanding what you think is wrong about this.
I thought you apply it to the lambda q only. Or the q and lambda q.
You thought we would only do it here on this q and not this one, you mean?
I guess.
Okay. Any ideas? I'm not expecting you to know the answer. I'm just curious if you have any thoughts about why this might not be what we want. Yeah?
First
So is this q a different q than this one? Yeah, they are, right? Why? Why do you think why do you say that?
Well, the other one's bound by
Right. This q here is bound by this lambda. So actually replacing this q doesn't really make sense. Because like this isn't really a thing named q, it's just like a thing that refers to this lambda. It doesn't really matter. I could call it lambda f dot f or lambda z dot z. It would be weird. We just said, oh, lambda z dot z should be the same as lambda q dot q. So it would be weird, if they're the same, it would be weird if in one case I replaced the q and in one case I didn't, just because it happened to be named q, right? So yeah, that's thing number one that's wrong, is we actually don't want to replace this q. So even though we're replacing q with this, we only want to replace free occurrences of q. Because the bound ones, they're not really named q in some sense. They could be named anything. They're standing there like to refer to a lambda, so we don't want to replace them. So number one, we don't want to replace bound occurrences of q. Anyone see what else is wrong? This one is a little more subtle. I'll give you a hint. It has to do with y.
The first lambda,
What about it?
refers to y, and then you're using y there. So it would
Yeah.
be calling back to that first lambda when you really want it to just be a free variable, right?
Exactly. That's right. I've changed the meaning of y by doing this, right? This y used to be a free variable. It was referring to something, who knows what, right? And now suddenly it's not referring to that something anymore. It's now bound by this lambda, right? So that's not good either. So we don't want to. This is called capture free variables. So that here. Okay. The solution to that is pretty simple. We notice, hey, I've got a free variable y here, so I better rename this lambda before I do the substitution. Because I can rename it. I can just say, oh, let's call it, lambda b dot q, lambda q dot. I actually don't even have any y's in here. But if I had y's in there, I could just change them all to b. And now I don't have a conflict anymore. Now I can go ahead and substitute, right? But again, it's something we just have to be careful about. All right, one at a time. So next time, we'll actually do some examples of reducing this. Yeah.
What would the
What was that?
So what would
The correct thing be?
Yeah.
Well, it'd be something like, first we have to rename the y, and then we just have to substitute for this q and not for this one. So the correct way to do this would be something like, lambda b dot yz, lambda t dot q. That would be like a correct substitution. Does that make sense? We'll go over this more next time and do some examples.